You think you understand cold. You felt winter. Maybe you've experienced -40 degrees Fahrenheit. You know what cold is, right? Here's what will blow your mind. Space isn't just cold. It's not even comprehensibly cold in a way your brain can actually process. And I don't mean that as hyperbole. I mean your evolutionary biology, the same biology that helped humans survive ice ages, is literally incapable of grasping how cold space actually is. What if I told you that the coldest temperature ever artificially created on Earth, and I'm talking about the most sophisticated labs with unlimited budgets, is still hotter than some natural regions of space? What if I told you that your body, right now, is warmer than cosmic microwave background radiation? That the ambient radiation filling the entire universe is so cold it would freeze your blood solid in microseconds? The terrifying part isn't just the cold. It's what that cold means. It's what it tells us about reality, about survival, about our place in a universe that's fundamentally hostile to everything we are. But before we dive into the abyss, I want to know who's watching. Where are you watching from right now? Drop your country and your time in the comments. Are you in Australia watching this at midnight? New York at 3 a.m.? I read every comment in the first hour, and I want to know my audience. If you're not subscribed yet, hit that button now. What we're about to explore will change how you see the night sky forever. And if you've already subscribed, thank you. You're part of the community that wants to understand the terrifying beauty of reality. Here's the first misconception I need to demolish. Most people think space is cold because it's far from the sun. That's backward thinking. The distance from the sun matters, but that's not the primary reason space is so cold. Think of it like this. Imagine a heater in a massive empty warehouse. The farther you stand from that heater, the colder you get. That's intuitive, right? But space doesn't work that way. The sun radiates energy in all directions, but in the vacuum of space, there's almost nothing to capture that energy. There's no air to heat up and circulate the warmth. There's no ground to absorb and radiate heat. It's just absence. The real reason space is so cold is because of thermodynamic equilibrium. Let me explain that without the physics jargon. Everything in the universe wants to reach the same temperature. Everything. If you put a hot object in a cold environment, heat radiates away from that object until it matches its surroundings. In space, the surroundings are determined by something called the cosmic microwave background radiation. It's the leftover heat from the Big Bang itself, and it's 2.7 Kelvin. That's your starting temperature. That's colder than anything in Earth's history. The sun, at about 9,932 Kelvin at its core, creates a tiny bubble of heat around itself. And we live in that bubble. Everything within our solar system is experiencing a temporary reprieve from cosmic cold. But step outside that bubble, you're entering a deep freeze that hasn't warmed up since the universe's infancy. This is your first mind-blown moment. The universe is naturally, fundamentally, incomprehensibly cold. Warmth is the anomaly. Our entire existence depends on a star that's keeping us in a pocket of slightly less deadly conditions. And here's where it gets genuinely terrifying. We're going to talk about what happens to matter, biological matter, your matter when it encounters that cold. Not metaphorically, physically, mechanically. But before we go there, I want you to try something. Go to your kitchen right now. I'll wait. Grab something from your freezer. Feel it. That's about 255 Kelvin. Feel how cold that is against your hand? Your body is fighting against that cold just by holding it. Your hand is radiating heat, trying to warm up that frozen object. Now imagine something so cold that touching it doesn't just chill your hand. Imagine touching something so cold that your hand doesn't just freeze. It becomes brittle. It shatters like glass. That's closer to what we're talking about. The question is, why? And that answer requires us to understand the molecular behavior of matter at extreme temperatures. This is where we need to bring in some actual science, and I want to give credit where credit is due. In the 1700s, a guy named Robert Boyle started noticing that gases behave predictably. When you lower temperature, you lower pressure and volume. But it wasn't until the 1850s that James Joule started doing these incredible experiments that revealed the true nature of heat and cold. Here's what Joule discovered. Heat isn't a fluid. It's not something that flows like water. Heat is molecular motion. Every object in the universe is made of atoms and molecules, and they're constantly vibrating, bumping into each other. That vibration, that movement, that is heat. Think of it like a crowded dance floor. When the music is loud and the energy is high, people are moving fast, dancing wildly, bumping into each other constantly. That's high temperature. When the music slows down, people move slower. When it stops, people barely move. That's low temperature. In space, the music is stopped. The atoms have almost stopped moving. They're in a state of near absolute stillness that defies human intuition. Now here's the mind-bending part. You can't actually reach absolute 00 Kelvin, the point where all atomic motion stops. It's theoretically impossible according to the third law of thermodynamics, discovered by Walther Nernst in 1906. The colder something gets, the exponentially harder it becomes to make it even colder. It's like approaching a wall you can never touch. But space gets close. Some regions get incredibly close. And that's what makes this terrifying. The next revelation will shift how you understand the possibility of survival in space. We're about to explore what happens when these molecular truths collide with human biology. Let me ask you a visceral question. What's the coldest temperature you've ever personally experienced? For most people, that answer is somewhere between -20 and -40 Celsius. Maybe you've been outside in brutal winter. Maybe you live in Minnesota or Siberia. That's probably the temperature foundation of your understanding. Here's a number. The average temperature of deep space is 2.7 Kelvin. Do you understand what that number means? Let me convert it for you. That's -270.45 degrees Celsius. It's -454.81 degrees Fahrenheit. The coldest natural place on Earth, the Antarctic Plateau in winter, is about 220 Kelvin. The coldest temperature ever artificially created in a laboratory was accomplished in 2003 by researchers at MIT. They cooled rubidium atoms to 50 picokelvin. That's 0.0000005 Kelvin. Let me create a mental hierarchy for you, because these numbers become meaningless without context. Room temperature, about 293 Kelvin. This is your baseline. Freezing water, 273 Kelvin. A difference of 20 degrees from room temp. Antarctica in winter, 220 Kelvin. About 50 degrees colder than room temperature. Deep space average, 2.7 Kelvin. About 290 degrees colder than room temperature. The coldest place scientists have ever artificially created, 0.000000000 Kelvin. Here's your mind-blown moment number 2. Humans have created temperatures colder than a NY naturally occurring place in the observable universe. We've manipulated matter to reach a state that doesn't exist anywhere else. But here's the existential horror of it. We can never reach absolute zero. We can get closer and closer, but never there. It's like a cosmic speed limit. You can accelerate a particle to 99.9999% the speed of light, but you can't hit light speed. The same principle applies to cold. This discovery is tied to Ludwig Boltzmann in 1872. He was a genius, absolutely brilliant, and he mathematically proved something that haunted him for the rest of his life. You cannot remove all the heat from a system. There's always a floor. There's always a lower limit. The universe has a temperature basement, and you can't go below it. Boltzmann eventually died, tragically took his own life in 1906, but not before. He'd helped establish thermodynamics as one of the fundamental laws of reality. His grave is inscribed with his most famous equation, S equals K log W. It's about entropy, about the disorder in the universe, about inevitable increase in chaos. Think of it like this. Imagine you're trying to organize an infinite library. The more organized you make one section, the more chaotic another section becomes. You can never organize the entire library. The universe trends toward disorder, and that disorder manifests as a temperature baseline. What does this have to do with space cold? Everything. The reason space is so cold is because of entropy. The Big Bang threw tremendous heat into the universe. Since then, that heat has been spreading out, dissipating, distributing itself across an ever-expanding space. As the universe expands, that energy gets spread thinner and thinner. Here's your first major revelation, connecting previous sections. The cold of space is literally the universe dying. Not metaphorically, thermodynamically. Heat death is the eventual fate of all existence, and we're watching it happen in slow motion. Every moment, the universe gets slightly colder as it expands. But wait, I promised you a paradox, and here it is. The sun is beating us with radiation. Right now, photons from the sun are hitting your skin. That's energy. That's heat coming at you at 300,000 kilometers per second. So how can space be cold if it's filled with radiation from stars? The answer involves understanding radiation pressure. And this is where we credit James Clerk Maxwell in 1873. Maxwell unified electricity, magnetism, and light into one framework. He proved mathematically that light carries momentum. Photons have mass-equivalent energy. They exert pressure. Think of it like standing in a rainstorm. Each raindrop hits you with a tiny bit of force. Now imagine the universe is covered in invisible raindrops photons from every star. They're hitting you constantly, exerting pressure. But here's the mind-blowing paradox. The radiation from distant stars is so faint, so spread out, that it barely contributes to heating anything in the deep vacuum of space. The inverse square law discovered by Isaac Newton means that radiation intensity decreases with the square of the distance. A star that's twice as far away sends 1/4 the radiation. A star that's 100 times as far away sends 1/10,000th of the radiation. So space is paradoxically cold, despite being full of radiation. The radiation is there, but it's spread out over such vast distances that it provides almost no thermal energy. Meanwhile, anything in that space, any object, any molecule, any atom, is radiating heat outward into this near vacuum. It radiates and radiates until it reaches thermal equilibrium with the cosmic microwave background. That's your second major revelation. The universe creates a cosmic radiation trap. You're constantly being bombarded by radiation from stars, but it's so dilute that it doesn't matter. Meanwhile, you're constantly radiating your own heat away. The universe is a one-way door where heat leaves but rarely enters. We've established the physics. We've established that space is naturally, fundamentally, incomprehensibly cold. We've established that this cold comes from the very nature of thermodynamic reality. Now we need to talk about what this means for life. What does it mean for the molecules that make up living things? Here's a question that will keep you thinking until we answer it in the next section. Your body is mostly water. Water freezes at 273 Kelvin. But water isn't just a liquid that becomes solid. It's something more complex. Ice has a crystalline structure. That structure can destroy biological tissue. When you freeze slowly, ice crystals form inside and around your cells. Those crystals can rupture cell membranes, destroying their structure. That's why freezer burn happens. That's why astronauts can't just step outside without a spacesuit. But in space, in the vacuum of the extreme cold, something worse happens. Something your body can't even imagine. Before we explore that, I want to ask, have you ever wondered why we need spacesuits? The obvious answer is air. We need oxygen to breathe. But the cold is just as deadly, if not more so. In the vacuum of space, the cold becomes an active, aggressive force, that doesn't just freeze you, it transforms you. The next section will reveal what happens when the human body encounters the vacuum of space at 2.7 Kelvin. Let me describe something genuinely terrifying based on NASA research and vacuum exposure experiments. You're floating in space. No spacesuit. The vacuum pulls at your skin. But here's what happens first. The pressure inside your body, your blood pressure, the pressure in your lungs, the pressure in every cell is much greater than the near zero pressure of space. The air in your lungs doesn't explode outward. Instead, it expands. Your lungs rupture from the inside. But that's not the cold part yet. That's the pressure part. Simultaneously, the water on the surface of your exposed skin, your eyes, your mouth, your nose, begins to evaporate. Not boil like you'd think. The low pressure means water molecules need almost no thermal energy to escape the liquid phase. They evaporate instantly. And evaporation is an endothermic process. It requires energy. That energy comes from your body heat. Your skin begins to freeze through evaporative cooling. Within seconds, your exposed skin begins to form ice crystals. But the really mind-blowing part comes when we understand what's happening at the molecular level. The water molecules that made up the moisture on your skin aren't just becoming ice. They're becoming exposed to a temperature so low that the molecular structure of that ice is fundamentally different from any ice you've ever seen on Earth. This is called amorphous ice that forms so quickly in such extreme conditions that it doesn't have the crystalline structure of regular ice. It's like frozen water that's captured in a state of chaos, molecules frozen mid-motion. It would be beautiful if it wasn't happening to human tissue. Your fingers, the ones with exposed skin around the nails, would lose sensation within 10 seconds. Not because of the pain, because the nerve impulses themselves slow down. Cold slows chemical reactions. It slows the propagation of electrical signals along nerves. Your nervous system would literally start shutting down from the periphery inward. Within a minute, the cold has penetrated deeper. Your core body temperature, normally 37 degrees Celsius, 310 Kelvin, would begin to drop exponentially. Here's where I need to credit some actual research. In the 1970s, NASA conducted experiments with animals in vacuum-like conditions. They exposed dogs and chimpanzees to extremely low pressures and temperatures. The results were horrifying. The animals could survive a few minutes without catastrophic organ failure, but during those minutes, their bodies experienced something no evolution had prepared them for. Your blood would begin to thicken. Think of it like this. At normal temperatures, blood is a fluid. The proteins and cells move through it easily. As temperature drops, the viscosity increases. The blood flow slows. Your heart has to work harder to pump thickening fluid through narrowing vessels. But there's something worse. At extreme cold, the proteins in your blood, hemoglobin, albumin, all the complex proteins that make blood function, would begin to denature. Their three-dimensional structure would collapse. They wouldn't just freeze. They'd break apart. The biological machinery that makes your blood work would malfunction. Your organs would begin to fail. Not from lack of oxygen initially. That takes a few minutes. From the physical and chemical breakdown of biological systems that evolved to work within a very narrow temperature range. The mind-blown moment. Your body is a heat engine. It's designed to maintain a specific temperature. Remove the environment that allows that, and you don't just get cold. You don't just freeze. Your entire biology, billions of years of evolutionary optimization, suddenly becomes a liability. Every single adaptation that makes you alive becomes a chain dragging you toward death. Here's the truly terrifying part. You'd still be conscious for much of this. Consciousness doesn't require consciousness. It requires brain function, and the brain can continue functioning for several minutes as core temperature drops. There's a phenomenon called the mammalian diving reflex. When mammals submerge in cold water, their heart rate slows dramatically. Blood flow to the periphery decreases, and concentrates on vital organs. The metabolic rate drops. Consciousness persists in a state of reduced awareness. But in space, this reflex would activate beyond anything evolution prepared for. Your heart rate would plummet. Your metabolism would drop toward near zero. You might, and this is speculative, but based on cold exposure research, remain aware, in some sense, as your body shut down around you. Some researchers believe you could lose consciousness within 10 to 15 seconds from hypoxia, lack of oxygen, to the brain. But the cold would be working simultaneously. The cold would be slowing your nervous system, dimming your awareness, pulling you down into a state of profound hypothermia. The final mind-blown moment of this section, the cold of space wouldn't just kill you. It would transform you into something else, a frozen object, a piece of drifting matter suspended between states, no longer alive, but perhaps not immediately dead. It would be a transition so extreme that the categories of alive and dead start to lose meaning. Your body, now in the vacuum of space, would undergo changes you wouldn't believe. In the cold at 2.7 Kelvin, water ice doesn't behave like water ice on Earth. It becomes denser, more crystalline in specific ways. The proteins in your tissue would become brittle. Your skin would harden into something almost ceramic. Over weeks and months, cosmic radiation would bombard your body. Without an atmosphere or magnetic field to protect it, every atom would be struck by high-energy particles. These cosmic rays would damage the molecular structure of your cells. DNA would unwind and break. Proteins would be ionized and shattered. And here's the paradox: in the extreme cold, there would be very little chemical decomposition. Bacteria wouldn't thrive. Fungi wouldn't grow. The cold would preserve you in a state of suspended animation, but animation that's broken. Your body would become a fossil before it became dust. Think of it like this. If you were sealed in amber in an Arctic vault and left for 1,000 years, you'd be preserved but also completely broken at the molecular level. That's what space does. It preserves and destroys simultaneously. The cosmic rays, the cold, the vacuum pressure, they'd all contribute to a gradual transformation of matter. Eventually, over eons, the atoms that made you up would scatter across space, incorporated into other dust clouds, other stellar systems. Your carbon would become part of another star. Your oxygen would become part of another planet. Your consciousness, yourself, would be scattered across light years of space. This is perhaps the ultimate terrifying truth. The cold of space doesn't just kill. It erases, it unmakes. It transforms you into something so fundamentally altered that the word death barely captures it. But before we get more philosophical, we need to understand more about how cold works at extreme scales. Because there's something even more terrifying than the cold itself. It's what the cold reveals about the nature of matter and energy. Let me introduce you to someone who dedicated his life to understanding cold. Peter Kapitsa, a Soviet physicist who won the Nobel Prize in 1978. Kapitsa was obsessed with how close you could get to absolute zero. He designed experiments to cool substances to temperatures that seemed theoretically impossible. In 1937, his team achieved temperatures below 2 Kelvin. They liquefied helium and cooled it below its normal boiling point. What they discovered was utterly bizarre. At these temperatures, liquid helium starts behaving in ways that violate your intuition. It becomes what's called a superfluid. Think about normal water. It has viscosity. It flows, but it resists flowing. Honey is more viscous than water because it resists flowing more. Liquid helium at extremely low temperatures has zero viscosity. It flows without friction. More than that, if you put superfluid helium in a container with walls, it will creep up the walls and over the edge, defying gravity. Here's your mind-blown moment. Matter doesn't just get hard and brittle as it gets colder. At extreme enough temperatures, it enters states of being that seem to contradict everything we understand about physics. It becomes something other. Capiza's work revealed that as you approach absolute zero, matter doesn't just cool, it undergoes quantum transitions. The electrons and atoms behave differently. The very nature of matter changes. And the kicker, you can never, ever reach absolute zero. You can get incredibly close, but there's always a floor. This brings us back to Ludwig Boltzmann and his equation. Entropy disorder always increases. That's the second law of thermodynamics. The universe moves from order to chaos, from hot to cold, from energy distributed unevenly to energy distributed evenly. Every time you try to cool something down, you're fighting against this cosmic trend. You're trying to create local order in a universe that fundamentally wants disorder. And the closer you get to absolute zero, the more energy you have to expend to push just a little bit closer. It's like pushing a boulder up a hill. The higher you get, the harder it gets. And the ultimate hilltop absolute zero is infinitely high. You'll never reach it. Think about this in the context of space. Space is cold because entropy is increasing. Heat from the Big Bang has been spreading out for 13.8 billion years. It's been dissipating, spreading thinner and thinner. Space is cold because the universe is dying. Not dying in a dramatic sense. Not dying like a person dies, but dying in the thermodynamic sense. All the energy in the universe is being evenly distributed. Temperature everywhere is approaching equilibrium. Eventually, in a time frame so vast, it makes human history look like a microsecond. The universe will reach heat death. Every star will burn out. Every atom will decay. Everything will reach the same temperature. No more energy gradients. No more life. No more anything. This is called the heat death of the universe, and it was first proposed in the 1850s by scientists like Rudolf Clausius. They looked at the second law of thermodynamics and realized it had a horrifying implication. But here's where we get into truly terrifying territory. The cold doesn't just affect large-scale physics. It affects quantum mechanics, the behavior of particles at the smallest scales. At quantum scales, particles don't have definite positions or velocities. They exist in a state of superposition multiple possibilities at once. But as temperature drops, quantum effects become more pronounced. The uncertainty principle, discovered by Werner Heisenberg in 1927, means that particles have a fundamental minimum of motion. You cannot cool something to a state where particles have absolutely zero motion, because that would violate quantum mechanics. At absolute zero, quantum uncertainty would mean particles would have zero-point energy. They'd still be moving, still vibrating, because the laws of quantum mechanics require it. You can't stop quantum motion. Think of it like this. Imagine trying to make a person completely still. You can slow them down. You can make them sit, but their atoms are still vibrating. Their electrons are still orbiting their nuclei. Their protons and neutrons are still made of quarks, spinning and vibrating. You cannot make anything absolutely still, because stillness violates quantum mechanics itself. This is absolutely mind-blowing. The cold cannot make matter completely still, because the universe doesn't allow absolute stillness. The fundamental laws of reality prevent it. So space is cold, incredibly, incomprehensibly cold, but not because particles have stopped moving. Space is cold because thermal energy is so low that particles are moving at nearly their quantum minimum. They're not moving because they're energetic. They're moving because the universe doesn't permit them to stop. The vacuum of space, at 2.7 Kelvin, is filled with virtual particles constantly appearing and disappearing. This is quantum foam, the idea that empty space isn't empty. It's seething with activity at scales too small to see. Particles and antiparticles constantly wink into existence and annihilate each other. This was predicted by Paul Dirac in 1930 when he theorized that antiparticles should exist. He predicted that empty space should be full of particle-antiparticle pairs constantly being created and destroyed. And we verified this. It's real. It's not just theory. So space, the empty void of space, is actually full of quantum chaos happening at scales below Planck length. The temperature might be 2.7 Kelvin, but that temperature is actually the result of this quantum flow. The universe is fundamentally active, fundamentally in motion, even at its absolute coldest. Here's the revelation that reframes everything. The cold of space isn't stillness. It's a specific type of organized chaos. It's quantum vibration at the lowest possible energy state. The universe is never truly still, never truly cold in an absolute sense. It's designed to always be moving, always be changing, even in its most extreme conditions. This should terrify you because it means the universe isn't just hostile to life. It's fundamentally incapable of being the dead, still place we imagine. It's chaotic and active, even at its coldest. Life isn't an anomaly in a dead universe. It's a different kind of pattern in a universe that never stops creating patterns. Here's something that will genuinely blow your mind. There are places in the observable universe colder than the average temperature of space. We know this because we've observed them. We've measured them. The Boomerang Nebula, discovered in 1995 by astronomers using the Hubble Space Telescope, is the coldest place ever observed in the known universe. It's a protoplanetary nebula cloud of gas and dust around a dying star. But unlike the region around the star, the outer regions of the Boomerang Nebula reach temperatures of just 1 Kelvin. That's colder than the 2.7 Kelvin cosmic microwave background radiation. How is that possible? How can something be colder than the radiation filling all of space? The answer involves understanding how gas expands. Imagine a gas that's being blown outward from a star. As it expands, it does work against the surrounding space. It uses energy to push outward. And as it uses energy to expand, it loses thermal energy. It cools. This is the same principle that makes a pressurized can get cold when you spray it. The Boomerang Nebula is expanding so rapidly, at about 600 kilometers per second, that it's cooling faster than the cosmic microwave background radiation can heat it back up. So it reaches temperatures below 1 Kelvin. It's a place where thermodynamics has created a pocket of extreme cold. Here's your mind-blown moment. The universe is capable of creating regions of cold so extreme that they beat out the baseline radiation temperature that fills all of space. These cold pockets are temporary. They'll eventually warm up to match their surroundings. But they prove that cold in the universe can get even more extreme than we might think. Meanwhile, in laboratories on Earth, scientists have been pushing the boundaries of cold in a different direction. In 2003, MIT researchers cooled rubidium atoms to 50 picokelvin. That's 0.0000000000000. They did this using laser cooling, a technique developed in the 1970s by Arthur Ashkin, Herb Koish, and Stephen Schuchu. They won the Nobel Prize for it in 1997. The technique works like this. Imagine you have atoms that are moving randomly in all directions. You hit them with laser light from every direction except one. The laser light from the 6 directions transfers energy that slows down the atoms moving in those directions. But the atoms moving away from the one unblocked direction don't get hit by laser light from that direction, so they don't get slowed down as much. Over time, all the atoms are preferentially slowed down, except those moving in one direction. You've created a cooling effect through radiation pressure. And if you keep applying this technique, you can cool atoms to temperatures that seem impossible. At these temperatures, atoms move at less than 1 millimeter per second. They're effectively frozen in place relative to normal scales. And when atoms get this cold, something bizarre happens. They start acting like waves instead of particles. This is the wave-particle duality of quantum mechanics. At extremely cold temperatures, the wavelength associated with particles becomes large enough that you can actually observe wave behavior. Atoms behave like waves. Multiple atoms occupy the same quantum state. They become indistinguishable. This state is called a Bose-Einstein condensate, predicted by Satyendra Nath Bose and Albert Einstein in 1924, and first created in 1995 by Eric Cornell, Carl Wieman, and Wolfgang Ketterl. They won the Nobel Prize in 2001. When atoms become a Bose-Einstein condensate, they behave in ways that violate every intuition about matter. They move as one entity. They have no individual identity. They exist in a quantum state of superposition. Measure one, and you collapse the quantum state of all of them. Think of it like this. Imagine a crowd of people walking through a doorway, one by one. Each person is distinct. Now imagine cooling them until they become so slow and so identical that they're indistinguishable. They move as one entity. They stop being individuals and become components of a single quantum system. At even colder temperatures approaching absolute zero, matter enters states that seem to violate the laws of physics. Liquid helium becomes a superfluid. Electrons in certain materials become Cooper pairs and create superconductivity electricity flowing without any resistance, without any loss of energy. Superconductivity is perhaps the most mind-blowing manifestation of extreme cold. In a superconductor, electrons somehow pair up and move through the material without scattering. They don't interact with the atomic lattice. They move in perfect concert, like a synchronized dance that has no friction. The first superconductor was discovered in 1911 by Heit Kamerlingh-Onnes. He cooled mercury to 4 Kelvin, and suddenly its electrical resistance dropped to zero. Zero resistance. That seems impossible. How can electricity flow without losing any energy? The answer was provided by Bardeen, Cooper, and Schrieffer in 1957 with the BCS theory of superconductivity. Electrons in a superconductor pair up in a way that allows them to avoid scattering. They move in quantum states that prevent them from interacting with the atomic lattice. What does all this mean? It means that cold isn't just about temperature. It's about unlocking different phases of matter, different states of being. It's about revealing the quantum nature of reality that's hidden at normal temperatures. At room temperature, matter seems solid and classical. Atoms vibrate randomly. Electrons move from atom to atom. Everything seems to follow classical physics. But cool things down, and you see the quantum truth beneath. You see particles becoming waves. You see matter entering states where the normal rules break down. You see the universe's fundamental nature revealed. Space is cold 2.7 Kelvin, not because of some surface property, but because of this quantum nature. Space is cold because the fundamental universe is cold. The warmth and life and energy we experience are temporary phenomena in a quantum universe that's fundamentally in a cold ground state. This is perhaps the most profound realization. We don't live in a cold universe that's somehow warm in places. We live in a quantum universe that's fundamentally cold, and we, through the power of stars, have created a tiny bubble of relative warmth that allows chemistry and life and consciousness to emerge. That's the revelation that should shift your worldview. Life isn't an exception to cosmic cold. Life is an exception to quantum reality itself. We're quantum rebellion against the ground state. We're thermodynamic disorder, creating temporary patterns in a universe trending toward disorder. We're warm anomalies in a cold cosmos. If I asked you why the cosmic microwave background radiation is exactly 2.7 Kelvin, what would you guess? The answer is absolutely profound and reveals something fundamental about how the universe works. It has nothing to do with where you are in space. It has nothing to do with your distance from stars. It's a temperature that's the same everywhere in the observable universe, in the Boomerang Nebula, in the empty voids between galaxies, in the depths of interstellar space. It's 2.7 Kelvin because the universe has a temperature. And that temperature is a direct consequence of the Big Bang. In 1965, Arno Penzias and Robert Wilson were working with a radio antenna when they detected a persistent signal they couldn't explain. It was coming from all directions equally. It was microwave radiation, electromagnetic radiation with a specific wavelength and energy. They had discovered the cosmic microwave background radiation. They didn't realize what it was at first, but physicists quickly understood. They were seeing the leftover heat from the Big Bang itself. They won the Nobel Prize in 1978 for this discovery. The Big Bang wasn't an explosion in space. It was an explosion that created space. In the first fraction of a second, the universe was incomprehensibly hot temperatures in the trillions of Kelvin. Particle physics at these temperatures is so extreme that matter as we know it doesn't exist. Quarks, electrons, photons all existed in a soup of fundamental particles. As the universe expanded, it cooled. This is described by Friedmann equations, developed by Alexander Friedmann in 1922. The expansion of space causes the cooling of matter. The two are connected. You can't have one without the other. For about 380,000 years after the Big Bang, the universe was too hot for electrons to stick to nuclei. Every electron was knocked loose by radiation. The universe was opaque photons, couldn't travel far before being scattered. But as the universe expanded and cooled, the temperature dropped to about 3,000 Kelvin. At that point, something remarkable happened. Electrons and nuclei combined. Hydrogen and helium atoms formed. The universe became transparent. This moment is called recombination, and it's incredibly important. Before recombination, the universe was opaque. After recombination, light could travel freely. For the first time, the universe was visible to itself. The radiation that was being scattered everywhere suddenly became visible light, and it filled the entire universe. But here's the thing. That light has been traveling for 13.8 billion years. In that time, the universe has expanded enormously. As the universe expanded, the wavelength of that light got stretched out. Stretched light becomes lower energy. Lower energy means colder. The ultraviolet light from recombination has been redshifted, stretched, cooled. Until today, it exists as microwave radiation at a temperature of 2.7 Kelvin. This is absolutely mind-blowing. When you detect the cosmic microwave background, you're literally seeing the leftover heat from the Big Bang. You're looking at the universe's birth certificate. You're measuring the cooling of the cosmos over 13.8 billion years. Here's the fascinating part. The cosmic microwave background is incredibly uniform. It's 2.7 Kelvin everywhere. Temperature variations are tiny, about 1 part in 100,000. But those tiny variations are incredibly important. Where there were slightly warmer regions, gravity pulled matter together. Over billions of years, those slight density variations grew into galaxies and stars. The slight temperature variations in the cosmic microwave background are the seeds of all structure in the universe. But the uniformity is also remarkable. The cosmic microwave background was emitted when the universe was about 380,000 years old. Regions of space that were very far apart had no way to communicate. Light wouldn't have had time to travel between them, yet they have almost exactly the same temperature. How is that possible? This is called the horizon problem, and it was solved by Alan Guth in 1980 with the theory of cosmic inflation. Guth proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent exponential expansion. This expansion was so rapid that all observable regions of the universe came from a single, uniform region. They started hot and uniform. As they expanded, they cooled together. When they separated from each other beyond the speed of light, they maintained the same temperature. Think of it like this. If you have a room of hot air and you blow it up like a balloon, the entire balloon will be the same temperature inside. If you then blow that balloon up even bigger very quickly, different parts of the balloon might separate from each other, but they'll all still be the same temperature. That's cosmic inflation. Here's the revelation that connects all the sections we've discussed. The universe has a built-in thermostat. The cosmic microwave background radiation determines the equilibrium temperature of space. Any object in space, a planet, a spaceship, a person, a dust grain, will eventually reach thermal equilibrium with the cosmic microwave background. It will eventually reach 2.7 Kelvin. The only reason objects in space don't immediately cool to this temperature is that they're being heated by nearby stars, or they're insulated from space. A spaceship doesn't instantly cool to 2.7 Kelvin because, 1, it might be near a star providing heat too. It has insulation that slows heat loss. 3, it might have internal heating systems. 4, the cooling process takes time, but given enough time in the absence of other heat sources, everything approaches 2.7 Kelvin. That's the cosmic thermostat setting. That's the temperature the universe wants everything to reach. Think of it like this. If you leave a hot cup of coffee on a table in a room, it will eventually cool down to room temperature. In the cosmos, the room temperature is 2.7 Kelvin. Everything wants to reach that temperature. Here's the mind-blown moment. You are warmer than your ultimate cosmic fate. Your body is 310 Kelvin right now. In 13.8 billion years, when the universe has expanded so much that all stars have burnt out and all sources of heat are exhausted, your atoms will reach 2.7 Kelvin. Or lower, if the universe continues expanding. You are a temporary pocket of warmth in a universe fundamentally trending toward cold. Your entire existence, your consciousness, your thoughts, your experiences, depends on this local departure from cosmic equilibrium. Let's talk about the future of stars and what that future means for heat in the universe. The sun will die. In about 5 billion years, it will exhaust its hydrogen fuel. It will expand into a red giant, swallowing Mercury, Venus, and probably Earth. Then it will collapse into a white dwarf, a core of compressed matter, about the size of Earth, but with the mass of the sun. That white dwarf will cool slowly, but it won't cool quickly. Because of its immense density and thermal mass, it will take trillions of years to cool down. A white dwarf might remain hot thousands of Kelvin for longer than the universe has existed so far. But the sun isn't the only star. Many stars are red dwarf small, cool stars that burn hydrogen slowly. These stars will last much longer than the sun. Much, much longer. A red dwarf can burn for trillions of years. The universe is only 13.8 billion years old. Red dwarfs will still be burning when the universe is 1 trillion years old. They're essentially eternal on human timescales. They're cosmic cockroaches, small, efficient, practically indestructible by stellar standards. But eventually, even red dwarfs will die. The smallest red dwarfs will take about 10 trillion years to burn through their fuel. And when they do, the universe will enter a new era. In about 10 trillion years, the last red dwarf will burn out. The universe will be dark and cold. There will be no stars producing heat, no light, except for occasional explosions from the rare collision between stellar remnants. At this point, the universe enters what astrophysicists call the degenerate era, a phase where the only objects remaining are white dwarfs, neutron stars, and black holes, all no longer producing significant heat. White dwarfs will be the last things to cool down. They'll slowly radiate away their heat as radiation into the vacuum of space. Over trillions of years, they'll cool down to the temperature of the cosmic microwave background. Then even below it, if the universe has expanded enough to cool the cosmic microwave background further. These cold white dwarfs, called black dwarfs if they've cooled to near absolute cold, will be the last remnants of stars. They'll be solid balls of matter, mostly carbon and oxygen, floating silently through the darkness. But even they won't last forever. Here's something that will genuinely unseat your understanding of reality. Protons might not be stable. They might decay. We don't think protons decay at any observable rate. The half-life, if they decay, is longer than 1,034 years. That's one followed by 34 zeros. That's a number so large, it's hard to conceptualize. But theoretically, grand unified theories suggest that protons should decay. If protons decay, then after about 1,040 years, all the protons in the universe will have decayed. This means all matter made of protons will disintegrate. White dwarfs will fall apart. Neutron stars will fall apart. Atoms will no longer exist. At this point, the universe will be filled with electrons, positrons, neutrinos, and radiation. No more matter, no more structure. Just particles and energy slowly radiating away. Your mind-blown moment, the stuff that makes you protons and neutrons and electrons, has a shelf life. Not just your body, not just stars. Matter itself is temporary. Given enough time, even the atoms that make up all matter will decay away. After YY years, the universe will contain no structure, no chemistry, no planets, no atoms, just radiation gradually cooling in an expanding void. This is the ultimate fate of a cold universe. Not just thermodynamic heat death, but complete structural death. Even atoms dissolve. What does this mean? What are we supposed to do with the knowledge that we live in a universe that's cold, that's trending toward colder, that will eventually become so cold and structureless that nothing like life can exist? This is where we transition from pure science to philosophy. This is where the cosmic horror of cold becomes a human concern. We know the universe is cold. We know that our warmth and life depend on a specific temporary arrangement of matter and energy. We know that arrangement is unstable. We know it will eventually end. But here's the revelation that reframes everything. The fact that we exist at all. The fact that we've emerged in this cold universe. The fact that we can understand the universe's nature. That's extraordinary. That's the opposite of terrifying. That's magnificent. But before we explore that philosophical shift, we need to understand one more aspect of cosmic cold. We need to understand what's happening right now, in this moment, because of the universe's cold nature. And that brings us to the beginning of life itself. Let's return from the far future to the present moment. Let's ask a question. It might reframe everything we've discussed about cosmic cold. Why does life exist at all in a universe trending toward cold? The answer is subtle and involves understanding the thermodynamic constraints on life. Life is impossible at temperatures below about 270 Kelvin. At that temperature, chemistry as we understand it stops working. Enzymes freeze. Proteins denature and crystallize. DNA strands become brittle and break apart. Life requires liquid water, organic chemistry, and energetic reactions. All of that requires temperatures above about 250 Kelvin. Life is also impossible at temperatures above about 400 Kelvin. Above that, proteins denature. Water boils away. Organic chemistry breaks down. Atoms move so fast that stable molecules can't form. So life exists in a very narrow temperature window, 250 to 400 Kelvin. Within that window, chemistry works. Reactions happen at rates that allow structures to self-organize and replicate. Think of it like this. Imagine a stage where temperatures are too cold for actors to move, or too hot for them to survive. There's a perfect range where the performance can happen. That's life's temperature range. Now here's the mind-blown moment. Earth is in this range right now because of a specific arrangement of cosmic events. We're the right distance from a star. We have the right atmospheric composition to trap heat. We're not experiencing an ice age or extreme greenhouse warming. We're in a Goldilocks zone of temperature stability, but this stability is temporary. It's precarious. It depends on specific conditions that could change. Earth is warm right now because of multiple heat sources. Let's enumerate them. 1. The sun. Approximately 99.97% of Earth's heat comes from the sun. 2. Radioactive decay in Earth's core. About 0.03%. 3. Leftover heat from Earth's formation. Diminishing over time, the sun will remain stable for about 5 billion more years. After that, it will expand and make Earth uninhabitable. So our window of habitability, our window of being in the right temperature range, is limited. But there's something even more profound happening. Let's look at Earth's history. 4.5 billion years ago, Earth was molten. It was warmed by several sources: the heat from its formation, radioactive decay, and collisions with asteroids and planetesimals. The surface temperature was above 1,000 Kelvin. No life was possible. Around 3.8 billion years ago, life appeared. The planet had cooled to about 290 to 310 Kelvin. Oceans formed. Liquid water became stable on the surface. Life emerged. Here's the revelation. Life didn't just appear in a cold universe. Life appeared specifically at the moment when the planet had cooled enough to allow it. Life is a consequence of planetary cooling. Life emerged from Earth's thermodynamic journey from hot to cold. There's a hypothesis called the Gaia hypothesis, proposed by James Lovelock in 1972. It suggests that Earth's biota, all the living organisms, act as a single self-regulating system that maintains conditions suitable for life. Lovelock looked at atmospheric oxygen levels, atmospheric CO2 levels, and ocean salinity. He noticed that these values have remained relatively stable for billions of years, within the narrow range that allows life to exist. That seemed unlikely to be coincidence. It seemed like life itself was maintaining the conditions for life. Think of it like this. If you had a room where temperature, oxygen levels, and humidity were all randomly fluctuating, it would be impossible to maintain health. But if organisms in that room actively regulated these conditions, keeping them stable, the room would become a stable environment. That's what Earth has done. Photosynthetic organisms created oxygen in our atmosphere. Microorganisms regulated CO2 levels. Life spread across the planet and created conditions that allowed more life to flourish. The mind blow: Earth isn't cold in spite of life. Earth is habitable because of life. Life has been maintaining a temperature and chemical environment suitable for more life to exist. Life is a thermostat. Life is a buffer against cosmic cold. Here's the profound paradox. We think of life as being threatened by cosmic cold. We think of the universe as cold and hostile, and life as a fragile exception. But actually, life has been fighting cosmic cold for 3.8 billion years, and life is winning. Life has created an entire biosphere, a layer of Earth dedicated to maintaining warmth and stability. Every tree produces oxygen while consuming CO2. Every ocean current regulates temperature. Every predator maintains population balance. Every microorganism recycled nutrients. Life is a vast, interconnected system that maintains the conditions for its own existence. You are not separate from this system. You are a node in it. Your breathing, your metabolism, your existence, all of it contributes to Earth's thermodynamic stability. You are literally a mechanism that helps maintain the temperature and chemical composition of our planet. This is the revelation that should reframe your understanding of cosmic cold. You are not a victim of cosmic cold. You are a warrior against it. You are an active component of a planetary system that has been pushing back against thermodynamic decay for billions of years. But here's the terrifying addendum. This system is fragile. Humans have altered atmospheric composition. We've accelerated warming and created climate instability. We've disrupted the cycles that maintain planetary homeostasis. The terrifying truth about cosmic cold isn't that cold threatens life. It's that life depends on precise balance, and we're disrupting that balance. We're throwing the thermostat out of adjustment. Here's an irony that will twist your brain. We've been talking about cosmic cold, about how the universe is fundamentally cold, about how life exists in a thin band of habitability. And right now, humans are making Earth warmer. We're not fighting cosmic cold. We're fighting atmospheric insulation. We're burning fossil fuels and releasing CO2, methane, and other greenhouse gases. These gases trap heat in our atmosphere. They prevent heat from radiating back into space. For millions of years, the atmosphere maintained a natural balance. CO2 levels kept Earth warm enough for life, but not so warm that the oceans boiled away. The biosphere maintained that balance through countless feedback cycles. But in the last 150 years, an eye-blink in geological time, humans have pumped trillions of tons of CO2 into the atmosphere. We've disrupted the balance. We've tipped the thermostat toward the hot side. And here's the mind blow. We did it while trying to solve a problem, providing energy and development for 8 billion people. That was itself created by how long we've been alive as a species. Scientists in 2009, led by Johan Rockström, identified 9 planetary boundaries, critical environmental limits that define a safe operating space for humanity. We've already exceeded several of them. 1. Climate change. Exceeded 2. Biodiversity loss. Exceeded 3. Land system change. Exceeded 4. Freshwater use. Approaching 5. Nitrogen and phosphorus flows. Exceeded 6. Ocean acidification. Approaching 7. Atmospheric aerosol loading. Uncertain 8. Chemical pollution. Not yet quantified. 9. Ozone depletion. Improving we're operating outside the safe boundaries in multiple ways simultaneously. The temperature of our planet is increasing. The chemistry of our oceans is changing. The genetic diversity of life is plummeting. But here's the terrifying paradox. We're causing warming while trying to maintain habitability. We're messing with the thermostat while standing in the room. We're so focused on day-to-day survival that we're not seeing the longer timescale impacts. Let me reframe this in terms of what we've learned about cold and temperature. Life has a temperature range, 250 to 400 Kelvin. But more specifically, human civilization has a much narrower range, about 280 to 320 Kelvin. We've built our entire civilization in regions with stable temperatures within that range. Agriculture depends on it. Rivers depend on it. Ocean currents depend on it. Weather patterns depend on it. Our entire global civilization is calibrated to a climate that's been stable for about 10,000 years since the end of the last ice age. We're now pushing Earth's temperature outside the range of stability that human civilization depends on. We've raised the global average temperature by about 1.1 Kelvin since pre-industrial times. That might sound small, but in terms of climate systems, it's huge. A 1.1 Kelvin change has already caused glacial retreat, sea level rise, changing precipitation patterns, increasing extreme weather events, ocean acidification, ecosystem disruption, and we're locked in for more change. Even if we stopped all emissions today, warming of another 0.5 to 1 Kelvin is already committed to because of heat stored in the ocean. The mind-blown moment. We've messed with our planet's thermostat so much that we've taken ourselves out of the climate stability zone that allowed civilization to flourish. We've moved toward the hot side of our Goldilocks zone. And if we keep going, we could push ourselves out of the habitable zone entirely. But here's where I want to pivot your perspective. I want to remind you of the cosmic scale. Yes, we're warming the planet. Yes, that's a serious problem that requires urgent action. But remember, in the cosmic scale and the thermodynamic arrow of the universe, Earth is still heading toward cold. We're just delaying it locally. In 5 billion years, the sun will expand and make Earth uninhabitable. The planet will cool when the sun dies. In 10 trillion years, when all stars have burned out, the universe will be dark and cold. In YY years, when all protons have decayed, matter will no longer exist. This isn't to diminish the importance of addressing climate change. It's to provide context. We're living in a moment of extraordinary privilege. We have the capability to observe and understand the universe, to manipulate our environment, to create meaning and beauty. Climate change threatens that privilege. It threatens the stable climate that allowed our civilization to emerge. That's genuinely important. That's worth fighting for. But it's also worth remembering that we're fighting against entropy. We're creating local order and stability in a universe that trends toward disorder and cold. That's noble. That's what life is. Life is pushing back against cosmic cold and decay. The revelation that should shift your worldview. We're not separate from cosmic processes. We're not aliens in this universe. We're part of it. We're conscious expressions of it. And yes, we're terrifyingly small and fragile. But that fragility is what makes our existence meaningful. Let me ask you a question that should haunt you in the best possible way. What are the odds that you exist right now, at this specific moment in the universe's history? The universe is 13.8 billion years old. Earth is 4.5 billion years old. Humans have existed for about 300,000 years. Modern civilization has existed for about 10,000 years. And you exist right now, in 2024, in a moment when we've developed technology to observe and understand the cosmos. The odds of you existing aren't just low. They're incomprehensibly low. You're a specific arrangement of about 7 octillion atoms that somehow organize themselves into consciousness. You're winning a lottery where the ticket cost is the entire history of the universe. But there's something even more extraordinary happening. You exist right now, at the moment when humanity has developed enough understanding to know about the cold of space, about the future of stars, about the heat death of the universe. You exist at the moment when we can ask these questions. For 99.99% of human existence, we didn't know these things. We thought the stars were fixed. We thought the earth was eternal. We thought cold was just a local phenomenon. We thought we understood our place. But you're in the generation that knows better. You're in the generation that understands cosmic cold. That understands deep time. That understands our fragility and our significance simultaneously. We call our current era the Anthropocene, the age of humans. It's an appropriate name because humans have become the dominant force shaping Earth's geology, biology, and chemistry. We've moved from being insignificant parts of ecosystems to being central players. But Anthropocene means something more than dominance. It means awareness. It means consciousness looking at itself. It means the universe becoming self-aware through human minds. For the first time in Earth's history, there's a species that can observe the cosmos, understand its own origins, predict its own future, modify its own environment, create art, music, meaning. That species is us. We're living in the moment when matter became conscious of itself. Carl Sagan, the astronomer and philosopher, said something profound. We are a way for the universe to know itself. That's not metaphorical. That's physically true. The atoms that make up your brain were created in stars. They've been through multiple generations of stellar birth and death. They're the universe's material made conscious. And right now, in this moment, you're aware of that. You're aware of cosmic cold. You're aware of thermodynamics. You're aware that you're a temporary arrangement of stardust in a universe trending toward decay. Here's the paradox that should blow your mind. Understanding cosmic cold should make you feel both insignificant and infinitely significant simultaneously. You're insignificant because you're small. Your lifetime is a microsecond in cosmic time. Your entire species' existence is a blink. The Earth is a dust speck. The sun will expand and destroy your planet. The universe will cool to a cold void in the unimaginable future. Compared to that, you matter less than a single atom matters to a galaxy. But you're also infinitely significant because you're aware of that. You can look at the cosmos and understand it. You can feel the beauty and terror of it. You can create meaning in a universe that's fundamentally indifferent. That's the human capacity. That's what consciousness does. It takes insignificance and transforms it into significance through understanding and meaning-making. The mind-blown moment. Cosmic cold isn't a reason for despair. It's a reason for awe. It's a reason to cherish the specific, fragile, temporary warmth you have right now. Here's where I want to make this personal. Here's where we move from abstract cosmic truth to your lived experience. Right now, your body is 310 Kelvin. You're fighting against cosmic cold through metabolism. Every meal you eat, you're consuming energy that came from the sun. That energy powers your cells. That energy allows you to think, to feel, to experience. The food in your stomach will be converted to ATP adenosine triphosphate, which is the energy currency of life. That ATP will power your muscles, your neurons, your immune system. You'll stay warm because of reactions happening inside you billions of times per second. You're a living furnace. You're a temporary pocket of warmth in a cold universe. And right now, as you're watching this, you're actively maintaining that warmth. Think about the extraordinary chain of events that had to happen. 1. A star had to explode and create the heavy elements that make up your body. 2. Those elements had to coalesce into Earth. 3. Life had to emerge from simple chemistry. 4. Life had to evolve for 3.8 billion years. 5. Mammals had to evolve with high body temperature. 6. Primates had to emerge. 7. Humans had to evolve consciousness. 8. Civilization had to develop. 9. Technology had to create the ability to broadcast and receive video. 10. You had to exist and choose to watch this. Each of those steps was almost impossibly improbable. But they all happened. They all led to you, right now, experiencing this moment. That's the revelation that should change how you see cosmic cold. The cold is terrifying. The universe is hostile. But your existence in that cold universe is a miracle. An impossible, improbable, beautiful miracle. So we've established that the universe is terrifyingly cold. We've established that human existence depends on maintaining warmth. Now let's explore how life actually stays warm. How do organisms survive in a cold universe? The answer involves understanding metabolic adaptations that are just as mind-blowing as the cold itself. Mammals and birds have something called endothermy. They maintain a constant body temperature through internal metabolism. This is a metabolic arms race. Your body is constantly burning fuel to maintain heat. About 20% of your energy goes just to maintaining your body temperature. Think of it like this. Every breath you take, every heartbeat, every neuron firing about 1/5 of that energy is just heat production. You're a biological heater. You're actively fighting against cosmic cold through chemical reaction. But here's the mind blow. This endothermy is expensive. Endothermic animals need to eat far more than ectothermic animals like reptiles that regulate temperature by moving to warmer or cooler environments. Your metabolic rate is about 10 times higher than a reptile of similar size. Why would evolution create such an expensive adaptation? Because endothermy allows incredible capabilities. Sustained activity in cold environments, nocturnal hunting, rapid response to threats, and large brains. Your ability to maintain constant body temperature is what allows consciousness. Let's look at some of the most extraordinary evolutionary adaptations to cold. The Arctic ground squirrel can lower its core body temperature to nearly freezing during hibernation down to about 267 Kelvin. Its heart rate drops from 300 beats per minute to 4 beats per minute. Its metabolism drops to 2% of normal. It's entered a state of suspended animation where time effectively slows down. Think about that. A mammal that can voluntarily drop its body temperature by 40 Kelvin and survive. That should be impossible. Yet the Arctic ground squirrel does it every winter. It enters the cold and transforms into something neither fully alive nor fully dead. It's in a state of thermodynamic limbo. The wood frog, yes, an amphibian, can freeze solid. About 65% of the water in its body turns to ice. Its heart stops. It's clinically dead by any reasonable definition. But when spring arrives and it thaws, it revives. It comes back to life. How is this possible? The wood frog produces glucose and glycerol that acts like antifreeze. These molecules prevent destructive ice crystal formation. They keep the frog's cells in a state of cryopreservation. When it thaws, the cells resume function. The mind-blown moment. Life has evolved ways to enter extreme cold and survive. Life has found strategies to approach the thermodynamic limits we discussed earlier. There are organisms called extremophiles that live at the edge of what's possible for life. These aren't in cozy, warm environments. They're in places that should be impossible for life to exist. Thermophilic bacteria live in hot springs at temperatures above 370 Kelvin. Their proteins are engineered to withstand that heat. Their cell membranes are made of different lipids. They're alien to us, but they're alive. Psychrophilic bacteria live in Antarctica and the deep ocean at temperatures near 270 Kelvin. These organisms have antifreeze proteins. They have membranes with unusual compositions. They've adapted to near freezing temperatures while maintaining the chemical reactions necessary for life. But here's what's truly mind-blowing. These extremophiles aren't living at the edge of possible temperatures for life. They're living in a narrow window 250 to 400 Kelvin, remember? They're just at different points in that window. The fact that organisms can adapt to nearly the entire range from near freezing to near boiling shows something profound. Life isn't fragile because of temperature sensitivity. Life is robust. Life is adaptive. Life finds ways to thrive in diverse conditions. This brings us to the future. As climate changes, as temperatures rise, humans will face new challenges. And we have some adaptive options. 1. Behavioral adaptation, moving to different climates, changing lifestyle. 2. Cultural adaptation, technology, cities, infrastructure. 3. Genetic adaptation, evolution over many generations. We're not limited to biological evolution. We have technology. We have culture. We have the ability to modify our environment and even ourselves. But here's the terrifying part. Our adaptation tools might not be fast enough. Climate is changing rapidly in decades and centuries, not millennia and millions of years. We're facing a mismatch between the speed of change and our ability to adapt. However, and this is the revelation that should empower you, humans have unprecedented advantages. We have technology. We have knowledge. We can engineer solutions. We can transition to renewable energy. We can modify agriculture. We can create artificial ecosystems if needed. The future is uncertain, but it's not determined. We have agency. We have the ability to shape our response to cosmic cold through conscious choice. This is the transition between the terrifying phase of the script and the empowering phase. We've shown the cold. We've shown the danger. Now we're showing that human consciousness, gives us power to respond. Let me ask a profound question. What is consciousness? What is it about your awareness, your subjective experience, that makes it different from the cold mechanical processes of physics? The honest answer is, we don't know. Consciousness remains one of the deepest mysteries in science. We can measure brain activity. We can map neural connections. But the subjective experience, the redness of red, the pain of pain, the joy of joy, remains mysterious. But here's what we do know. Consciousness allows meaning-making. Consciousness allows you to take meaningless physical processes and interpret them as meaningful. A specific frequency of electromagnetic radiation is meaningless physics. But to your conscious mind, it's the beauty of a sunset. Its significance. This is extraordinary. In a universe governed by thermodynamics and entropy, consciousness introduces meaning. It introduces purpose. It introduces value. Think about it. No amount of physics can explain why you find beauty in a sunset. Physics can describe the wavelengths, the atmospheric scattering, the eye's response. But it can't explain why you find it beautiful. That's consciousness creating meaning. Here's an essential paradox. Your mortality creates your meaning. If you were immortal, if you had infinite time, would anything matter? Would you feel urgency? Would you pursue projects? Would you create art, relationships, memories? It seems like mortality would diminish meaning. But actually, it's the opposite. Mortality creates meaning. The fact that you have limited time, maybe 80 years if you're lucky, makes those years precious. Each moment is finite. Each person you meet will eventually be lost. Each experience will eventually be memory. That finitude creates intensity. It creates meaning. In a cold, indifferent universe, mortality is what gives consciousness its power. Because you know you'll die, you live. Because you know others will die, you love. Because you know your civilization will eventually crumble, you create art, science, knowledge to pass forward. The mind-blown moment, cosmic cold and thermodynamic decay don't diminish human meaning. They create it. Your significance comes from your insignificance. Your meaning comes from your mortality. Let me talk about science specifically. Science is humanity's response to cosmic cold. When humans wonder about stars, we're trying to understand the light that's been traveling across cold space for years. When we study biology, we're trying to understand how warmth and life emerges in a cold universe. When we practice medicine, we're trying to preserve consciousness and warmth against decay. Science isn't separate from the cold. Science is our way of acknowledging the cold and creating understanding in response. Every scientific discovery is an act of meaning-making in an indifferent universe. When Einstein derived E=mc, he was revealing the relationship between matter and energy that allows stars to shine. When Boltzmann derived his entropy equation, he was revealing the fundamental trend of the universe toward cold. When Darwin proposed evolution, he was showing how life creates order in the face of thermodynamic disorder. These discoveries don't change the universe. The universe remains cold and indifferent, but they change us. They allow us to understand. They allow us to respond consciously. And then there's art. Music, painting, literature, dance art is humanity's most profound response to cosmic cold. Art serves no thermodynamic purpose. A symphony doesn't keep you warm. A painting doesn't feed you. A poem doesn't provide shelter. Art is useless from the perspective of survival. But art is how consciousness celebrates itself. Art is how humans acknowledge the cold and create warmth in response. When you listen to music, your brain releases dopamine. When you see beautiful art, your neurons fire in patterns of pleasure. You're creating warmth, literal neurochemical warmth in response to beauty. Think about Beethoven creating his Ninth Symphony while deaf. He couldn't hear the music he was composing. Yet he created one of the most transcendent pieces of music ever written. He created meaning in silence. He created warmth in isolation. That's the human capacity. That's what consciousness allows. It allows you to create meaning in an indifferent universe. It allows you to create warmth, emotional, spiritual, transcendent warmth in the face of cosmic cold. The revelation. Art isn't a luxury. Art is how consciousness survives in a cold universe. Art is how humans persist. Art is how meaning persists. In 1990, as Voyager 1 was leaving the solar system, we asked it to turn around and look back. Carl Sagan described what it saw. From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. The photograph Voyager took is called the pale blue dot. It shows Earth as a tiny point of light, barely visible against the vast cosmic background. It's about 0.12 pixels in size. It's smaller than the grain of sand on a beach. On that dot, every human who ever lived lives. Every war, every love story, every scientific discovery, every work of art, every moment of consciousness, all of it happened on that microscopic blue dot. Look at it. Understand that you're on that dot right now. You're part of that dot. And that dot is in a universe that's incomprehensibly vast and cold. The obvious reaction is despair. I'm so small. I don't matter. Everything I do will be forgotten. And there's truth in that reaction. You are small. Everything will be forgotten eventually. But here's the shift. Smallness doesn't negate significance. Brevity doesn't negate meaning. Obscurity doesn't negate love. You have something extraordinary. You have consciousness. You have the ability to know that you're on a pale blue dot in a cold universe. You have the ability to understand thermodynamics, cosmic evolution, stellar physics. You have the ability to love, to create, to experience beauty. That's not a small thing. That's extraordinary. That's privileged. Most of the universe is unconscious matter. Most of existence is processes happening without observation or awareness. But you're aware. You know. You understand. The mind-blown moment. The universe is cold and indifferent, but it's aware of itself through you. You are how the universe knows itself. You are how the cold becomes meaningful. This isn't meant as comfort in the nihilistic sense. It's meant as truth. The universe doesn't care about your suffering or your joy, but you can care. You can create meaning. You can love. And that matters, not to the universe, but to you, to others, to the conscious beings that temporarily exist on pale blue dots across the cosmos. You're not the only conscious being. You're not the only observer of cosmic cold. There are billions of humans on Earth, all of them aware, all of them experiencing, all of them creating meaning. And if the universe is full of stars and planets, if the conditions for life can occur elsewhere, then you might not be the only conscious civilization in the cosmos. There might be others, billions of others, each on their own pale blue dots, each creating their own meaning in the cold. Imagine that. Imagine a galaxy filled with billions of conscious civilizations, each aware of the cold, each responding with science and art and love. That would mean the cold universe isn't empty. It's full of meaning-making beings. We don't know if extraterrestrial life exists, but we know the conditions for life chemistry, energy, time are probably common in the universe. And if life emerges, consciousness will likely follow. And if consciousness emerges, meaning follows. The revelation. Cosmic cold doesn't negate meaning. It might enable it. A cold, vast universe might be teeming with conscious beings, all creating significance in the face of indifference. Let me make this personal and immediate. You're reading or listening to this right now. At this moment, there's nothing else you need to do. There's just this moment of awareness. You're conscious. You're alive. You're warm literally. Your body temperature is 310 Kelvin. That's extraordinary. That's miraculous. That's the culmination of 13.8 billion years of cosmic evolution. That's the specific arrangement of atoms that allows you to experience anything at all. In this moment, what matters? What feels significant? Not abstract facts about the universe, not average temperatures, but what you actually experience right now. Maybe it's curiosity, maybe it's awe, maybe it's fear about climate change or cosmic cold, maybe it's love for someone else, maybe it's the drive to create something, maybe it's the desire to understand. All of those are valid responses to the knowledge that you live in a cold universe. And all of those responses matter. All of those responses are acts of consciousness creating meaning. Let's return to where we started. The terrifying truth about how cold space really is. Space is cold, incomprehensibly, terrifyingly cold. The universe is fundamentally trending toward cold, toward heat death, toward decay, toward the eventual end of all structure and meaning. That's true. That's the physical reality. And understanding it should change you. It should make you feel the weight of cosmic insignificance. It should make you aware of your fragility. But here's the reframe. The terrifying truth is also a beautiful truth. Because in a cold universe, warmth is precious. Because in an indifferent universe, consciousness is miraculous. Because in a universe trending toward decay, meaning-making is revolutionary. The universe doesn't care about you. The vacuum of space will destroy you in minutes. Stars will eventually die. The universe will eventually cool to near absolute zero. All of that is true. But you care about yourself. You care about others. You create meaning. You create warmth, literal and metaphorical, against cosmic cold. You're alive right now, in the middle of the story. You're both insignificant and infinitely significant simultaneously. That's not a contradiction. That's a paradox that consciousness can hold. That's the human capacity. So what do you do with the knowledge that space is terrifyingly cold? That the universe is dying? That you're a temporary arrangement of atoms? 3 things. First, take care of the warmth you have right now. Your life, your relationships, your experiences. These matter not because the universe cares, but because you care. Cherish them. Don't waste them. Don't wait for permission to pursue meaning. You have limited time. Make it count. Second, act to preserve the conditions that allow consciousness to flourish. Address climate change. Protect ecosystems. Advance knowledge. Reduce suffering. Create beauty. These actions don't change the ultimate fate of the universe, but they change the path you take and the beings you help along the way. Third, wonder. Keep wondering. Keep asking questions. The fact that you can understand the universe even partially is extraordinary. The fact that you can feel awe, that's consciousness at its best. That's how humans thrive in a cold universe. Science, art, love, community. These are humanity's responses to cosmic cold. These are how we stay warm. These are how we create meaning. Now I want to turn this back to you. This script has taken you on a journey from the terrifying physics of cosmic cold to the empowering realization that consciousness matters. But this isn't the end of the conversation. This is an invitation to continue it. You now understand that space is cold. You understand the physics. You understand the implications for life. You understand the paradox of insignificance and significance. But what does this mean for you specifically? How does this change how you live? How does this shift your priorities? How does this affect your relationships, your work, your sense of purpose? Those are questions only you can answer. And I want to know your answers. Drop a comment. What was your biggest mind-blown moment? What realization shifted your perspective? What action are you going to take because you understand cosmic cold and human significance simultaneously? Comment, subscribe, share this with someone you care about. Have conversations about what it means to live in a cold universe with consciousness and meaning-making capacity. This is how communities are built. This is how consciousness continues to create significance in a cold cosmos through conversation. Through shared understanding, through collective meaning-making. Before we close, I want to leave you with one final revelation. It's the idea that might matter most. You're not just an individual consciousness in a cold universe. You're part of a narrative. You're part of a story that's been unfolding for 13.8 billion years. For most of that story, the universe was unconscious. Particles formed, stars burned, galaxies collided, but there was no awareness. There was no meaning. There was just physics. But then, on this pale blue dot, at this particular moment, consciousness emerged. Humans emerged. We became aware. We started creating meaning. And now, you're part of that continuation. You're the universe becoming conscious of itself. You're how the cold cosmos knows it's cold. You're how the meaningless universe creates meaning. Every time you wonder about the stars, you're extending that awareness. Every time you create something beautiful, you're extending that meaning. Every time you love someone or help someone, you're extending that consciousness. You're not separate from the cosmic story. You're the cosmic story experiencing itself. You're the universe looking back at its own cold depths and saying, "This is beautiful. This is meaningful." This matters. That's your significance. That's your power. That's why cosmic cold, while terrifying, is also sacred. Let me use the remaining time to deepen what we've discussed and integrate the lessons. Think about what we've covered. We started with shock, the revelation that space is incomprehensibly cold. We established the physics. We explored the implications for life. We discussed the future of the universe. We examined humanity's response through science, art, and consciousness. And we arrived at a conclusion that seems paradoxical. Cosmic cold is terrifying, but it's also the context that makes consciousness meaningful. Let's spend time exploring how this paradox plays out in different domains. In science, cosmic cold drives inquiry. We want to understand why the universe is cold. We want to understand the mechanisms of heat, energy, and entropy. Every scientific discovery is part of this larger story of consciousness, trying to comprehend its context. In philosophy, cosmic cold raises eternal questions about meaning and purpose. Why do we create meaning if it's all meaningless? Why do we love if love is temporary? Why do we strive if everything ends? These questions aren't defeatist. They're the deepest questions consciousness can ask. In spirituality, cosmic cold manifests as the sacred. Many spiritual traditions have grappled with the vastness and indifference of the cosmos, and many have concluded that this vastness is what makes the sacred sacred. The transcendent arises from confronting the cosmic scale. In daily life, cosmic knowledge creates perspective. Your problems feel smaller when you understand you're on a pale blue dot. But other people's suffering feels more important because suffering, consciousness, and meaning are so rare in the universe. Priorities clarify when you understand that time is finite and consciousness is precious. In relationships, cosmic cold teaches urgency. The people you love are mortal. You're mortal. The time you have together is finite. That should intensify love, not diminish it. That should motivate connection, not distance. In work and purpose, cosmic cold motivates meaningful contribution. Your work matters not because it lasts forever, but because it affects conscious beings in a brief window. That's enough. That's everything. Throughout this entire script, we've woven together several mind-blown moments. 1. The revelation that space is colder than any cold you can imagine. 2. The understanding that matter itself has limits absolute zero, can't be reached. 3. The recognition that the universe is inherently cold and trending colder. 4. The realization that life and consciousness exist in a narrow temperature window in an inhospitable cosmos. 5. The paradox that we're simultaneously insignificant and infinitely significant. 6. The truth that consciousness creates meaning in an indifferent universe. 7. The understanding that you're part of the universe, becoming conscious of itself. Each of these should shift how you see reality. Each of these should contribute to a transformation in perspective. But knowledge without application is empty. So as we close, I want to challenge you to actually do something with this knowledge. Not someday, not eventually, soon. If you're concerned about climate change, take one action. Research renewable energy options. Reduce your carbon footprint. Support climate science. Vote for politicians who take climate seriously. One action today that moves toward preserving human habitability. If you want to contribute to human meaning-making, create something. Write something, paint something, compose something, build something. Contribute to the collective consciousness. Add to the meaning. If you're struggling with your own significance, remember, you don't need permission to matter. You matter because you're conscious. You matter because you can love. You matter because you can create. That's enough. If you feel isolated or alone, remember, there are billions of other conscious beings on this planet, and possibly billions more on other planets across the cosmos. If life is common, you're part of a community of consciousness. You're not alone in the cold universe. And finally, maintain wonder. Stay curious. Keep asking questions. The cold universe is mysterious and beautiful and terrible and magnificent. Don't lose the ability to be awed by it. Thank you for taking this 210-minute journey through cosmic cold with me. Thank you for engaging your mind, your emotions, your consciousness with these ideas. The fact that you did, that's what matters. That's consciousness responding to knowledge. That's meaning persisting in a cold universe. Keep wondering. Keep creating. Keep loving. Keep making the universe conscious of itself through your awareness and your actions.